What? Oh.
So it's recording.
Okay.
Okay. So this is the final talk of today's discussion session. So we are very happy to have the Dr. Syo Kamata from MCBJ. He is going to give a talk on Degenerate Weber Stokes graph and its application. And it's deeply related to the previous talk by Nao. So you can ask questions even during the talk. So please.
Okay. Okay, thank you for the introduction. First of all, I would like to thank organizers to give me this opportunity for this talk. So today I'm talking about the Degenerate Weber Stokes graph, which is kind of extension from the ARA type Stokes graph, and also we would like to show its application. So this talk is based on this paper, which will appear soon, I hope. And collaboration with Syo, Miss Misan, and Mr. Tsunzel. All right, so first of all, so this talk is basically based on the previous analysis talk. And so first of all, let me summarize his talk. And I'm somewhat assuming that the audience was listening to his talk. Okay, so in his talk, his main motivation is getting the quantization constant and solving it, basically by using a double potential. So in this case, we usually start with a Schrödinger equation, or what? And then we draw the Stokes graph, okay? And get a quantization condition by using connection formula and yeah, this kind of Stokes graph. And one of the good advantage is this kind of quantization condition can be expressed by the both multiplier. So we call them cycle. And using this DDP, by using DDP formula, so we can make resurgent solution, and also we can reproduce the cancellation of discontinuity, okay, coming from the Borel non-summability. And also by only from this quantization, we can make the out of expression like generalized Bohr-Sommerfeld quantization condition and the spectral form of the partial function and Gutzbert-Foss formula and path integral, and also it's related to the less extendable. Okay. Okay, now let us focus on the quantization constant. So in this case, D, so this is quantization constant, and basically this can be expressed by the cycle, part of the cycle A and non-part of the cycle B, and these are the function of H bar, and now this carry E is energy, okay? So now this, as I said, this A is basically the part of the cycle oscillation around vacuum, and also D is basically a tunneling effect. Okay, and also this can be defined by some routine integration by using S odd. Okay, what? Okay, but one of the important point is that, okay, so when the genus one case, like the double world potential, so this can be expressed by hypergeometric function, and also to get this higher order of A or B by using derivative of E acting to the hypergeometric function, so we can get some form of E in terms of E. For each order of H bar. So this topic was told by the Gokshibazawa talk, and also it's arguable in this kind of, yeah, this paper. Okay, but usually, okay, we cannot get this kind of sound form. So if the sound form is unavailable, there is a mismatching with the known result, for example, Jin-Justin result. In the case of Naoshi, he didn't use that kind of sound form. So in that case, for example, if you want to solve the quantization potential and getting non-part of F to the energy. So there is a mismatching. So this epsilon, delta is a solution by using this equation. So in his case, he arrived at this form. But if you see the Ginger student paper, so there is H bar over 2. So very, very roughly speaking, the motivation in my talk is we want to solve this mismatching. That's all. Very simple. Okay. Okay, but as I said, in general, it's very difficult to get that kind of the sound form, like a hypergeometry function. So if you want to extend to the higher genus case, one has to fix this problem. But the problem is, okay, the question is why this problem appears. So the answer is the applicability of the ARA Stokes graph. So usually, once we have the potential and energy, so we can make a Stokes graph using the leading order of Q, let's say a V minus E, okay? So, but now E, energy isn't what? Okay, sorry. E is nothing but a free parameter before solving the quantization condition. So in this case, we expand this E by using this kind of form expansion of in terms of H bar. Okay, so from 0 to infinity. Okay, but if you solve this equation, okay, why? So immediately we can see that this E is starting with H bar. Okay. So this is basically just the Hammond postulator, but even in this case, this starting with H bar. So H0 equals 0, and H1 here, H1 is K plus 1 over 2. Okay. Okay. So as I said, this Stokes graph is related to E0. And in this case, from the aspect of the dynamical system, the E0 is now the control parameter of the Stokes graph. So meaning that there is a bifurcation when E0 is 0. Okay. So when E0 is larger than 0, so we have ARA type Stokes graph like here, 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 and we have a 4 turning point, and also each of them is a single turning point. However, if we choose E0 equals 0, okay? So in this case, this turning point is closing to each other. And finally, we arrive at this one, okay? Which is a double turning point. So usually this type of the Stokes graph is called as Degenerate Weber Stokes graph. Okay, so of course, if we arrive at here, so the connection formula is different from the ARA type Stokes graph. So naively thinking, we have to start with this type of the Stokes graph when at least when solving the quantization condition, and it starts with order H bar. Okay, so roughly speaking, the assumption of this guy was violated. Okay. Okay. So as I said, so in this case, the Degenerate Weber Stokes graph should be considered when energy is starting with order H1, order H bar. Okay. And also, as I said, it's very difficult to get the standard form of in terms of E. So in that case, in the case of genus one, we can get this kind of form. However, if you want to go to the higher genus, it's a really difficult problem. So in this talk, because of this motivation, we would like to show the review of the Degenerate Weber, the connection formula, and also, as a simple application, we would like to apply this Degenerate Weber connection formula to the Suji deformation quantum mechanical system. Okay. Okay, so first of all, let us get the connection formula of the degenerate Weber type. So, okay, so we have to, we would like to take this step. So basically, this process is basically the same as ARA type. However, this Schrödinger equation, only this Schrödinger equation is different. So in our case, we start with this form, okay? So here, this is kinetic down, and also now we have the like mass down, and also here, this is energy. But now in this case, kappa is introduced, and this is a coupling with H bar, okay? And then, and also in the case of ARA type, so this part, okay, is just X, okay? But now in the case of degenerate Weber type, so it has this kind of form. And then we would like to get the connection formula. Let's say this is local one. And finally, we will this connection formula to our potential. Let's say it's global Stokes graph. Okay. So, yeah, actually, this derivation is a really complicated and technical. So I briefly explained how to do it. Okay, so now, as I said, we start with this, so the Schrödinger equation. And in this case, this gives this kind of Stokes graph. So here, this is turning point. And now it has 1, 2, 3, 4, the Stokes line. And now we call these only 1, 2, 3, 4, anticlockwise. And also we put label plus, minus, plus, minus, and in this case, minus, plus, minus, plus. And now in this case, we have 2 independent solutions. So we label this solution psi plus and psi minus. And one of them is basically exponential going up. And also the other one is exponential damping factor. So in this case, this psi plus has exponential going, which is dominant. And if you rotate pi over 2, then this the psi minus is dominant. And this has an exponential damping down. So, okay, so we consider these 2 types. Okay, so okay, so now what? Why so? Okay, so now we want to get the formal solution of this Schrödinger equation. So now firstly we redefine this wave function by using u. This is given by this. And by using explicit calculation, so we can get this kind of formal solution. And now this coefficient is given by the Poco-Hammond symbol, and depending on kappa, this one. Okay. And also important factor is that now this wave function u has a Gaussian type, something like this. So this is the main difference from the ARA type. Okay, then let us add Borel transform B. So in this case, now this H bar is replaced by Borel parameter C. And also, yeah, actually, this can be expressed by this form. And eventually, this can be again written by the Gauss hypergeometric function f, and this the parameter and s is given by here. Okay, and also by using the formula of the hypergeometric function, so this can be written by u minus plus regular. But now we are interested in the singularity of the Borel plane. So we need to consider, we don't need to consider this regular part. So, okay. So now let us act the Laplace transform. So, and take a Hankel contour. So because now it has here, it's minus, for example, here has a singularity. So this gives a non-trivial value. So now here, U plus, UB plus, UB plus, and now it gives a UB minus here, okay? So yeah, this is basically the connection formula. And now important fact is that it has a gamma function denominator and also depends on kappa here. Okay, but in this case, this is just a 1, 4 to 1. But if you want to get the connection formula for the 1 to 2, 2 to 3, 3 to 4, so it can be obtained by rotating this coordinate y to the pi exponential pi I over to y, for example. So it gives eventually u plus 2, u minus, u plus 2, u plus, u plus 2, u minus, etc., etc. Okay, so yeah, this is a summary of the local connection formula. So in this case, we consider two types, and now this upper index corresponding to left panel and lower index corresponding to right one. Okay, so in this case, for example, if consider the 1, 4 to 1, so this psi plus gives this psi minus, okay? Because now this is the dominant part and this is subdominant part, damping down. Okay, and also, okay, so in this case, this psi minus is has an exponential growing term. So yeah, this is this psi plus is exponential damping down. So this yeah, plus minus is flipped. And also this kappa is also good. So it's okay, so we could get a local connection formula. Then we would like to map this connection formula to our potential, our case. So in this case here, for example, if you consider the 4 to 1, now we put this kind of answers. So now it is X. This is global wave function global potential. Here it is local potential. And now, now we replace this kappa with F. And also we put C. So this C is basically coming from the arbitrariness of the normalization. Okay. Yeah, and also, yeah, this E is okay. Now in your we want to consider the energy starting with order H bar. So yeah, we really define this energy like this form. So here. Okay, so our task is the getting relation between kappa and F here. And also to calculate this C. Okay. Okay, so in order to get F and C, so we would like to use this relation. So this relation can be obtained by expert calculation, basically. So for example, now Qx is basically V minus energy, potential minus energy, and now X is a global coordinate and Y is a local coordinate. And now we expand this Y using, yeah, this kind of form. So what quotient of Y is the function of X. And now this is a Schwartz derivative. Okay, and also, once you have a potential, global potential, of course, by using a Riccati equation, this S and Q can be obtained. So, but now from now, basically, we would like to use only first one and third one. So, okay. Okay, so first of all, let us consider the relation between kappa and F. Okay, so now we put this formal solution and that. And now Q is defined by V minus E and proportional to H bar. And actually, this V can depends on H bar, for example, like the Suzy quantum mechanical system, as we will show later. Okay, then in the usual way, let us expand this S by using H bar like this one. And now we have, because now we have a two independent solution, so we can get two different plus minus two independent solution from this square root Q0. And also the higher order of S can be obtained by this form based on the Riccati equation. And now we define S odd and S even by using kind of this average or minus. And actually, if this V, it doesn't depend on H bar, and this E doesn't couple with H bar, this odd has only odd power of H bar. Let's say -1, 1, 3. However, now it has this H bar dependence here and here. So it sort of can have the even power of H bar. Okay. And also S even has also the odd power H bar. But actually, this S even can be expressed by only expressed by S odd. So actually, important part is only S odd. So this wave function can be expressed by integration of S odd, and there is the 1 over square root S odd by using this form. Okay, so okay, so from this S odd local from the local potential, this has this kind of form like H bar -1 and minus kappa over Y plus blah blah blah. And if you take the residue, residue integral around Y equals 0, so actually this gives kappa minus kappa here, because now this Y is the numerator, and okay, and also this gives basically 0 under this residue integration. And also for the global potential, okay, let us define F like this form. So now where the AR is a turning point. So why this is so? Okay, and also by using this relation, okay, so we can arrive at the residue is local S odd is equal to the residue integration of the S odd obtained by the global potential. So finally, we can get kappa equal F. So yeah, this plus minus is a little bit the technical coming from the technical reason. Basically, it's coming from the asymptotic behavior or the Stokes graph. But important fact is actually this F can be obtained by this residue integration around the turning point. Okay. So we could make the relation between two. Okay, so next one is a calculation of this C. And to do it, we use this one, this relation. Okay, but now once we have the potential, global potential, so we can get QX. So by using this relation, we can make a relation between the Y and X here. Okay, from this. So this is a leading order. And this second one is next ordering order of this relation. And also, if you want to consider higher order, yeah, by using this, yeah, you can execute your, you can explicitly write down it like this one.
Sorry, can you remind me what's S odd minus 1?
S odd here? Ah,
Yes.
okay. This is the leading term of S odd. So the, okay, wait, maybe it's better to go, yeah, here. So this is minus 1, okay? So S order is basically, yeah. So this guy, this is S order, if n equal minus 1.
Can I then, the next slide, the page 20. So here you write an expansion on top, with H bar is only on the first term.
Here?
There's no more H bar dependence of the S odd?
Yeah, it has, of course.
On the order y minus 3, meaning it's
yes, of course. Okay, yes. Okay, and okay, maybe from here, okay. Okay, and also by using, and also the wave function of x and wave function of y, it can be related to like this form. And also now psi, these psi can be explained by using S odd, like exponential integral. Why is this? So this y is coming from here, and this guy is coming from this guy here. And now we could get a relation between y and x and just input here. So by solving this C order by order, then we can get this precise form for your, from the given potential, global potential. Okay. So this is summary of the connection formula. So if, as I said, if we consider the cross, for example, from 1 to 1, so yeah, it corresponds, yeah, this connection matrix is given by this, and basically this, as I said, this C plus C1, C minus can be calculated by the previous technique, and also F is also calculated by Regge integration around the turning point. Okay. And if you flip this sign, okay, so this component is gonna be opposite here, from here to there, and also this F is also flipped, something like this. Okay, so this is a connection formula what we put. Okay, so here, so now we could get the connection formula or the degenerate Weber type, but we have one question. Okay, so actually, and for example, in the analysis, so we could get the quantization condition, for example, using the cycle from the ARA type. Okay, but now we could get the connection formula, and of course from that we can get the quantization condition. But the problem is how much we can get, how much we can transfer his result, ARA type result, to the Degenerate Weber type. So actually, the answer is all of cycle expression does not change. So we can keep the cycle expression by making the dictionary. So for example, if we can keep, get the dictionary, let's say between the cycle between ARA type and Degenerate Weber type. So by naively replacing A to, let's say, fractal A and fractal B, so we can make the result of the Degenerate Weber type from ARA type. So from now, we would like to make this dictionary. Okay. So, okay. So let us make this dictionary. So first of all, focus on the consider a cycle. So okay, so in this case, okay. So here, this is a cycle of the ARA type. So in this case, one here, ARA type, ARA Stokes graph here, and now it has a 2 turning point. But if we take the E equals 0, E0 equals 0, let's say, how this is closing each other, and finally we can arrive at here. Okay, so this gamma is roughly speaking this orbit. But actually, in this case, this is just going to be residue integration. Sorry. Yeah, like this. So in this case, we can easily make this dictionary between the A cycle of the ARA type and the Degenerate Weber type. Okay, so the B cycle is a little bit more complicated. So in this case, let us consider this Stokes graph, okay? And also in this case, once we take the E equals 0, so here this has actually here this is another ARA type graph, and once you take E equals 0, so these two turning points is closing to each other, so finally we can get, yeah, we can arrive at this one. So basically, yeah, differences, these two differences, what? Yeah, the E0 is the positive or 0. So now let us take this orbit here, consider this orbit. What? So here, this orbit. And actually, so by using connection formula of ARA type, this n minus here and change turning point, and n minus here, and again changing turning point. So we can get kind of one over here. And in the same similar way, we take this orbit, and by using the connection formula of the Degenerate Weber type, firstly we cross here and changing the turning point here, and again cross here, and again we go back to the original turning point as a normalization. So in this case, also we can get kind of Mondoli matrix here and compare these components. So maybe easiest way is look at D1 to 1, D21. So in this case, this D21 only depends on depends only on this B cycle. Okay. So originally the definition of the B cycle is this integration like this, and basically it's essentially the same as twice of integration from here to there. But if you look at this part, yeah, you can arrive at this. You can get this form. Okay. So this is dictionary. So in this case, because this B cycle is intersected with 2A cycle, this has an information of F, which is the information of the A cycle. And also here, this is an exponential damping term. Okay, so here, this is the dictionary. Okay, so by using this dictionary, the result X by cycles can be directly transferred from the ARA type to the Degenerate Weber type. So just replace this A, B by using this one and this one, sorry, this guy. Okay, so yeah, from ARA type, we can get the concentration constant of the Degenerate Weber type, and also directly we can get. Wait, sorry, why it's happening so much? We can DDP formula can be also reproduced by the replacing with this our new cycle definition. Okay, and also by considering this quantization constant, so we can immediately get this kind of the quantization constant, which is basically consistent with the Gene-Justin result. Okay. Okay. How we say how? 10 minutes. Okay. Okay, so I finished the basic of the Degenerate Weber test. So let us apply this technique to the quantum mechanical system. So in your case, let us consider this potential. So now W is a super potential, and also it has also the derivative of super potential proportional to H bar here. And if you take this P is 1 or minus P, so this is a this system resisted supersymmetric case. But now we take this P as a real value. Okay, but now let us fix this super potential. So in our case, we consider double wave potential like this, and also triple wave potential like this. And because of this, the plus minus P proportional to H bar, so this minimum is going down or going up. Okay, so this distance from 0 is proportional to H bar. Okay, and also here is the graph of the triple wave, and also this distance is proportional to H bar. So if you fix P equals 0, so this is nothing but the usual double wave and triple wave. Okay, so as I said, sorry. Yeah, from the definition of the A cycle and B cycle, so we take this form. And now this B0 is the bioenergy here. And also there is some the quotient C and F here. And because this B cycle is intersecting with two cycles here like this. So B cycle is here, and A cycle here, here, and this B cycle here, A cycle here, here. So this B cycle intersect with the two A cycle. So this is information of these two cycles. Okay. So if we take A prime 0, it denotes the left one, and if we take A prime is 1, it denotes the right A cycle. Okay, so in similar to the ARA type, we can get quantization constant. So yeah, this is basically explained by the Untitled Stokes, I guess. Yeah, just replace this A cycle and B cycle with, using our dictionary. And also the quantization constant of triple wave can be obtained like this form. So yeah, this is a little bit more complicated. And now, okay, so and this plus and minus is the sign of the complex phase of the H bar. Okay, so for some technical reason, let us redefine this A cycle and B cycle like yeah, this form. Okay, so in this case, now if you look at what, sorry. So if you look at what, sorry, what happened here? Sorry. Wait, sorry. Okay. Okay, so for example, if you look at the a cycle here, and look at and also look at F. So it is always sorry, wait, what? Something. Okay, so in this case, the linear order of F can depend on the P here, so which is basically proportional to H bar in the potential. So it is always +1 or -1 or 0. So we define this F so that the leading term of F bar does not have this speed dependence. So this is always +1 or -1 or 0, at least in the case of the supersymmetric case. And also we do the same thing for the B cycle. Then, so in this case, the A cycle, A1, A2 can be written by this form. So A bar times, and L is sorry, if L equal 1 is the left one, and if L equal 2 is the right part of the cycle. So actually, this can be written by this, and also by looking at the leading order of that, then yeah, it's written by this form. And also it can be, it's a doable. It is doable for also the non-part of the cycle, and also yeah, it can be written like this form. And in the case of the triple well, so A cycle, A1 cycle and A3 cycle is basically the same. But A2 cycle, central cycle is a little bit different from the A1 and A2. But in this case, in your case, this A2 can be written by A bar square. So this can be checked by explicit calculation. And also, yeah, by using the definition of B bar, so it can be also written like this form. Okay. And the important thing is that in this case, because now we have two independent vacua for the triple well. Actually, this difference is corresponding to the inner vacuum or outer vacuum. But on the other hand, in the case of the double well, basically this curvature is basically the same. So that's why this coefficient is same. However, in the triple well, this coefficient is slightly different. Okay, so by using this definition, let us consider the quantization condition by using this new definition A bar and B bar. And yeah, this can be written like this form. Okay, but now important factor is that now this quantization condition can be expressed only by A bar and B bar in both cases. Okay. So essentially, this triple well potential could be reduced to the double well and triple well could be reduced to the genus one system by using this new definition. And also, yeah, DDP formula for A bar and B bar can be expressed by this one, and we can make sure that yeah, imaginary ambiguity is cancelled by using this relation. Also, this is upper index. Okay, so by using this relation, let us consider the non-perturbative contribution to the energy spectrum. But now let us firstly focus on the perturbative part. So perturbative part is given by this form, and now look at leading order, then yeah, this can be written like this form. And in the case of triple in the similar way, so this has this form. And one of them is if this solution of E can be obtained by one of them is 0, here is 0, or here is 0. What? Okay, so yeah, by looking at this, so you can immediately this energy spectrum. in the part for the part of the part. And now K is the energy level. And in the case of triple well, so we have two vacuola, so inner vacuola and outer vacuola. So and also the curvature of energy, curvature of the minimum is a little bit different. So that's why this has 1/2 or proportional to 1 something. Okay, so in order to obtain the number of the contribution, so we add epsilon h bar to this part of the solution here, and by putting this boundary condition, by boundary condition. Okay, so if we look at the double well potential, so in that case, this delta is obtained by this equation. So finally, by solving this equation, so you can get this solution. Okay. So for example, if P is the integer, so this is this has an energy splitting coming from the instanton, like epsilon here. But on the other hand, if P is not integer, so it doesn't have any energy splitting, and it's a starting with buying energy, buying sector. Okay. And also we can consider triple well in the case of triple well. Okay. So, but now we have two vacua, inner vacua and outer vacua. So each of them gives a different form, different different equation for getting this delta. So, for example, if we consider inner vacuum, so this solution is coming from this one, and if you see the outer vacua, so this is given by this form, this equation. Okay, so the solution is given by this form, so which is really very complicated. So here is a solution of inner vacuum, and now it's proportional to B0, and here is a B0 square, it's right. And of course, there is the imaginary ambiguity, plus minus here. Okay. And if you see the outer vacuum, so what? Yes, yeah, we can do the same thing for outer vacuum. And so this solution is given by like this form. Okay, but in this case, when the P is not P, P is not 2q plus 1 over 3, where q is integer. So in this case, this has an energy splitting coming from this epsilon. So this is the main difference between the when p equals 2q plus 1 over 3 or something. Okay, should I finish my talk here?
Yeah, I think you can continue.
If you can.
Okay, thank you, thank you. Okay, so finally, okay, so let us consider Down's relation. Okay, so basically Down's relation is in the language of in our language, this is nothing but a relation between among A cycle, B cycle, and energy. So in the case of double well, so we can the quantization condition is given by this form, and basically this f was is the function of E and H bar. Okay, but now let us change the independent variable using f. So now originally this fg was a function of E, but now by using this f as a the fundamental variable, then this E is a function of f, and also this G is a function of f. So and it is known that we can get this kind of relation in the double well. But now this is a conjecture. But in the case of W, it has this kind of form. Okay, then let us consider our case, like in the P deformation quantum mechanical system. Okay, so in order to consider Down's relation, we have to change this form by using G, like this form. So yeah, this is a little bit complicated form. However, if we use the F bar and B bar, so this set can be written like this form. So here this is G, and here F bar, and now this is here there is a H bar over 2 and F bar, blah 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 blah. So let us start with this form. Okay, so by explicit calculation, by using real calculation, so that we can get this kind of form depending on E. And also by using coordinate transformation, the G can be also obtained like this form. And here is a double well. This is triple well. And now let us change the variable, fundamental variable E to F. So this can be written by this form. And also in the case of triple well, so we have, as I said, we have, okay, so now in this case, we look at only outer vacuum. So this can be written like this form, okay. Okay, so by looking at this relation, actually we can arrive at this form here like this. So essentially this is same as a double well. Even when the SUSY double well. But now in the case of double well, as I said, we have two vacua, so meaning that it has a two energy. So we can get the two relations like this. So here it's a relation of the down relation of the inner vacuum. Here it's a relation of the outer vacuum. So yeah, this is the kind of extension of the down relation for the SUSY quantum mechanical system. Okay, so here is summary. So in this talk, we explained basically of Degenerate Weber Stokes graph, and yeah, it is generally necessary when considering quantization condition and also the higher genus. And also we showed the small application to the P deformation SUSY model for the quantum tilted double well, triple well potential. We consider non-particle transition energy, and also we consider down the relation. And also, actually, for example, if you want to consider the kind of the relation between the hidden topological angle of the partition function and mass of index, actually by using the definition like A bar, B bar, actually we can make this relation explicitly. And also by using this, for example, QSI exactly solvable. Yeah, this kind of thing can be also considered by starting with the Degenerate Weber. Okay, that's all. Thank you for attention.
Thank you so much for a very exciting and beautiful talk. So now this session is open for questions, discussion, and any kind of comments.
May I ask one thing?
Okay, go ahead.
I'm not familiar with the details of the exact WKB, so let me ask just a simple question. From the beginning, I got an impression that by choosing a energy variable E, the ARA type Stokes graph can be turned into the Degenerate Weber type. So at this point, it looks just a technical stuff. And so the final result of physical quantity like the bound state energy spectrum or partition function should not depend on your choice of the ARA type, Stokes graph, or Degenerate Weber type. So if that understanding is correct, could you tell me the advantage or necessity to choose either Degenerate Weber type or ARA type Stokes graph?
So for example, my first motivation was how to solve this problem. So once we consider the ARA type, so yeah, actually this coefficient doesn't happen. So yeah, this is a very naive motivation starting with the Degenerate Weber type.
So does it mean that
I have a comment.
okay.
Actually, it looks different. However, the spectrum doesn't change. Actually, the definition of B in ARA's case and definition of B in Jean-Dustan's case or Degenerate Weber's case are different.
Interesting. I see. So,
Such
so this
difference,
means,
and also yes.
So does it mean that the
and also the
again,
definition of okay.
A choice of ARA type or Degenerate type it does not affect physical quantity at all?
Yeah, exactly.
Interesting. I see. So why should we? I mean, what's the? It is of course interesting to study Degenerate Weber type, but are there any particular advantage or necessity to choose either one of them?
Either one.
I mean, either ARA type or Degenerate Weber type.
Okay, but for example, when considering solving energy spectrum, so it could be obtained after solving the compensation question, right? So usually, as I said, it depends on the H bar in the first the reading order. So yeah, naively speaking, we should start with this as a naive mathematical logic, right?
Yeah. Well,
for example, if you want to obtain the hidden topological angle with this exact WK method, then we have to choose Degenerate Weber method.
I see. I see. That's a good advantage. Okay. Okay. Thank you.
Can I ask a question?
Mm-hmm.
So your Degenerate Weber equation, which is on one of the next pages that you have here.
Degenerate Weber equation. This guy, this one.
Yes. So this is just a parabolic cylinder equation, and we know all the connection relation for these special functions. So why do you need lots of your analysis? Because the connection relations from one side to the other side is known using the parabolic cylinder functions.
You mean uniform WKB, for example?
You don't need WKB. I'm just saying you can just do it directly from the special functions that we know. If you express them on one side in terms of the parabolic cylinder functions, the connection relations are known for the parabolic cylinder functions to the other side, and hence you know also what happens with the connection relations.
Yeah, but in that case, usually we firstly flip the potential, right? From the plus and minus, and
all those connection relations are known. Those functions are known globally. So.
Oh, really?
Yeah. Parabolic cylinder functions are well-known special functions. If you take the Borel transform, you will get the hypergeometric functions, but in a way it's not needed because we know everything about parabolic cylinder functions.
Yes, indeed, it's true for this equation. This Weber equation, but we want to consider global potential, not experiment double well to do such stuff. So the basic Degenerate Weber equation is just a local analysis of our global potential, like W-Weber such stuff. So to obtain the connection formula for generic potential, not only, Weber potential, then we have to,
Okay, so
do
yeah,
this
so
calculation.
yeah, of course, if you just want to get the connection formula of this, yeah, of course it's known, but it isn't enough for our motivation. So we want to, yeah.
Okay, thank you.
Okay, yeah, thank you for your comment.
I have a question.
Okay, please.
Basically, a follow-up. So if I understood correctly, you used this Aoki-Kawai-Takei type transformation series.
Yes.
To go from the canonical equation to the more general. So initially, this series is just a formal series. Do you have any analytic interpretation, a rigorous interpretation of the transformation series?
Sorry, which one?
There, back one. Yes, the yx h bar equals sum of y and x h to the n.
Oh, you mean physical interpretation, for example. So yeah, this is nothing but just a change of coordinates. So yeah, for example, yeah, if you want to, let's say, the conformal mapping, for example, so you need to use this derivation. So yeah, at least in my case, this is nothing but a change for the change of coordinates. That's it.
My question is, is there an analytic meaning to that power series in H bar? Because to me, it looks like it's just initially a formal series.
Analytic meaning.
Of course, it's formal sheet, but of course, we consider the Borel summation.
Okay, then did you prove that it is Borel summable? And if yes, on which domains in the X?
Yes. Borel summability depends on the imaginary term of H bar. So it's same to the Aries case. I mean, when the two Stokes curves connecting each other, in such a case, Borel summability, yes, the wave function doesn't Borel summable. I mean, such discontinuity is encoded to DDP formula.
Okay, I understood that, but that's for the WKB solution. What about the transformation series itself?
Sorry, maybe I don't understand your question so correctly. So
there is a series relation between X and Y variables, which is given in the middle of this slide on the right-hand side. Yx h bar equals sum.
Here.
What is the meaning of that series?
What is
it a convergent series or Borel summable? If it's Borel, can you prove that it's Borel summable?
I see.
Which domains of the X variable?
I see. Oh. Okay. Yeah, well, I think basically this is a Borel summable. Otherwise, it has exponential summing or something, right?
So the borosibility of S, or I mean, this quantity is analyzed by DDP formula and the Stokes curve. This is enough, I think. If you want to know the Stokes phenomena correspond to H bar, then the DDP formula determines it. And if you want to know the Stokes phenomena of X, then Stokes curves determine it. So both conditions are determined. Each region is, boresomble or not.
I'm not convinced yet. So you want S and S hat to be some proper analytic functions, right?
Yes.
Then the Y as a function of X has to be an analytic function as well. But
Yes.
the formal series is not necessarily an analytic function. So you need an analytic meaning to that initially formal series.
Oh.
So that S becomes a composition of S hat, an analytic function, plus Y, another analytic function.
Okay. Sorry, I cannot make answer right now. Yeah, so at least in my motivation, what we want to know is the analytic property of the wave function, psi plus and psi minus. Yeah, that's it, basically. And using that, we want. So yeah, actually, for example, from this property, we made a kind of the function of the A cycle, B cycle, like condensation constant, looking at only DDP. By looking at using DDP formulas, we made a kind of relationship between the quantization constant having H bar, complex plus complex. Positive complex phase or negative complex phase or something like that. So yeah, that's it actually we consider.
Okay.
Kamata-san, actually Ines gave a question in my talk. She asked how to calculate the quotient of trans series. I mean, it means the way to calculate the quotient to F and other stuff. I mean, page 37 maybe.
37. Here, 37 here. Hello, now it's up.
Yes. Oh, sorry, much more late. 40, 47, 46.
This one? This is about the downs relation.
Yes, I mean, yes, this one. Or the latter one is also fine. I mean, maybe the latter one is better.
This one?
Anyways, okay. So this F0, F1, F2, or in the previous slide, E1, E2, E3, or such stuff is, HY expansion of F, right? So this HY expansion, so this one is quotient of, omega in my torque.
Yes.
So yeah, this is the quotient So in terms of energy eigenvalue, not partial function, then this result is nothing but the quotient of Laurent series. So in essence, the question is how to calculate this quotient easily.
This one.
Yes.
So yeah, basically this is coming from the residue integration. Okay. So yeah, in the sense, if you want to go back to the ARA type, so this replaced by the E over H bar or something. At least this is doable for only for this is doable for the parametric cycle. Then you can make
4G, yeah.
And G, so I haven't checked for G. Yeah, maybe it's probably it's doable. Yes. Yeah, but now in this case, this is coming from the degenerate Weber type. But for example, if you go back to the ARA type, at least A cycle is fine. It's just replaced by E. Also, this E by E over H bar. It's okay. But to be honest, I don't have confidence whether this is working for G.
Well, maybe to answer her question, then we may explain the Merin transform and the related stuff.
So what do you mean?
You know, to use Merin transform.
Hi. Yes. Yeah, actually, yeah, by using Merin trans, yes, there is another way to get this quotient C by using Merin transform. Yes, but today I didn't explain that. Yes. But now, yeah, I don't have a slide to explain that right now.
Where could I find it?
It's written by the Jean Justin paper, and also DDP, and DDP paper. They were considering this technique too.
For the Degenerate Weber?
Yes. Yeah,
actually, it's a bit complicated. In Jean Justin's paper, he didn't use this exotability method, but his method is applicable for our situation.
Yes. Yeah, but this is essentially the same as calculating C for all orders. But if you use the Merin transformation or that kind of technique, this calculation can be easily. And explicitly, you can make a kind of relationship between the A cycle of the B cycle of ARA type and Degenerate Weber type. Yeah.
Or we will publish our paper about this stuff future, maybe soon, hopefully. So in this paper, of course, we will write how to derive the quotient using Merin transform.
Yeah, this paper, which will appear soon, we hope.
Worst case scenario, I'll ask you to just explain me at some point just a bit more of the gory details about that. Doesn't need to be right now. But thank you.
Yeah, no problem.
Just, again, I think that it comes from the same thing, but in the same slide, I think 47. Yes. So this E0, E1, E2. So these are the expansions. This is the coefficients of the expansions in H bar as well.
Yeah. Yes.
Yeah. Okay.
Yeah. Zero order, first order, second order. Yes. So this is yeah, roughly speaking, this is an instant one, a biome energy, because now it's -1 and 0, 1, blah, blah, blah. Yes.
And in your, sorry, I just have another question. In your calculations, so how general the potential can you use for the equivalent of the degenerate Weber calculation? So we were talking about that there was the basically harmonic oscillator type, but you say that for more general, meaning this would work for general potentials. How general would they be?
Yeah, and wait. Yeah, for example, this one.
But here would be, yeah, so, but here is, so 2 ARA type graphs, 1 degenerate Weber, right?
Yes, yeah, basically, yeah. When considering the solving quantization condition, yeah, maybe this situation is coming from always, yeah, this type, yeah, change, I think. So for example, if you consider triple Weber and false Weber, actually this has a 1, 2, 3, 4, or more, 3, 4, 5. So yeah, eventually, yeah, this is gonna be, yeah, once you choose this parameter, then it's gonna be like this one. Yeah, so yeah, basically, so in this sense, this is a kind of small extension of this kind of graph, as far as solving, yeah, this problem, solving quantization condition.
I believe that, yeah, something happened. Can't even. That's so. If you can hear me, yes, I can handle the rest. It seems that that's I had some issues with the camera and microphone at the moment, but I can't even reply. No, it's there was just an issue. Sorry, nothing related to the discussion. Yes, but I couldn't even answer to you via chat for some reason. Tatsu, sorry, he was just mentioning that he's having some issues. In any case. Any other questions or comments? We can hear you.
Okay.
Any other questions or comments from the rest of the people? We can also.
Yeah, may I have a question?
Yes.
So, so if you have more than 2 turning points collide each other, do you expect a similar formula?
Sorry, say again, please. Sorry.
Yeah, more than 2 turning points. So for example, 3 turning points collide.
1, 2, I see. But for example, okay, so for example, let's assume we have originally 3 ARA types. Okay, but in this case, it has 1, 2, 3, 4, right? So, but now if we have 3, maybe it's gonna be, I don't know, how many, 6? 1, 2, 3, 4, 5, 6. So maybe this number is different, I think. So in this sense, yeah, we have to make, yeah, maybe it's a different, it is a different connection formula if this number of Stokes line is changed. So it-
similar problem happens if you consider the superpotential in this case you consider the superpotential has a simple zeros, but if you consider the simple zero collides, you get the similar problem for.
Okay, so as far as the concern, yeah, of course it depends on the form of potential. But for example, if the super polynomial is just let's say polynomial, so this is always this kind of change. So yeah, in that I don't think this is just I don't think different type colliding doesn't happen. It's always this kind of from 2L to 1. Yes, for example, at least if W is a polynomial X, yes, but if you consider much more complicated cases, I don't know.
Okay, thank you.
So let me ask a related question. As a potential, if the bottom minimum is like harmonic oscillator quadratically one, but suppose this is a third order, then or fourth order, for example, then when the energy is tuned to this particular bottom, is it just a Weber type or different?
Wait.
W equal X to the fourth, and you are tuned to X.
W equal X fourth.
Energy is tuned to 0.
Energy is tuned to 0. Yeah, in this case, I think. Wait. So in this case, so okay, equal 0. Just X fourth. Wait. Yeah, I think so. Yes. Okay, sorry, so W equals just an X force, right?
Well, as a potential, not W. If you have, say, a double well potential whose maximum is going to be 0, then it is a quartic potential. And it looks, when you tune the energy to this particular value, 4 zeros, 4 turning point looks to be degenerate. That's what I meant.
Okay. Point is.
Yes. So in this case, the system is not degenerate Weber, but much more degenerate.
I see. I see. Okay, that can happen. Okay, right.
Sorry, I couldn't even write that. Yeah.
I can have a comment on that. So I think then the solutions will be described by Bessel equations or Bessel functions if you have a fourth order. So as you suggested, X to the fourth, for example. So there is a paper by Frank Olver from 1955, I think, or 56, where he describes the uniform behavior near a higher order turning point of the WKB solutions. And he expresses the solutions in terms of I and K Bessel functions.
Okay.
That's very interesting. On the other hand, suppose there are so much various complicated situations. can you give me any guidelines to choose, say, ARA type or Degenerate Weber type or any other complicated ones? It seems that ARA type is sort of generic. So why not choose just ARA type?
Why not choose just the ARA type?
Yeah, by appropriately choosing energy value, generically we get ARA type, right?
No, okay,
Seems
so
to me.
okay, yeah, but okay, so if you just start with the Schrödinger equation, as I said, is just nothing but a free parameter, right? So we can make a ARA type or the Weber type, etc., etc. But now, in your case, we are looking at the solution of the quantization function.
But do I understand correctly? If we are looking for quantization condition and subsequent bound state spectrum, it doesn't matter which choice of Stokes graph we start from.
But this problem was happening, right?
Yes. So okay, indeed. So the two quantitative condition looks different, but actually equivalent. However, to solve for delta, which is non-productive contribution to energy, then in the case of above one, actually the function B also depends on delta. I mean, because in the case of ARA types, the all B both multiplier also depends on energy. So to solve for delta is very difficult in the above case.
I see. Could you remind me what was delta?
Delta is non-productive contribution. I mean, maybe the previous slide.
I see. Something like a hidden topological angle. Is that the way?
No. So it's
the reading of delta is instanton amplitude in that case.
I see.
so, yeah, this one, this guy.
And you solved for delta maybe in the latter slide or something.
I see. So this means the final result of energy is independent of any choice of Stokes graph, but the division to into a perturbative contribution and non-perturbative contribution depends on your choice. Is that the way?
Division.
Well, I mean, it appears to me that your delta may be important, but doesn't appear as a single entity to the final physical result. That's what you said, right?
Yes.
So if delta is a sort of defining the significance of non-perturbative contribution, then the physical quantity such as energy spectrum remains independent of the amount of delta. But if you want to decompose into perturbative and non-perturbative contributions, the definition of each term may depend on your delta. Is that the way?
Yes.
Yes.
I see. It's very subtle.
Yeah, so if you want to consider just the formal fraction function or DDP formula or such stuff, then you don't have to consider Degenerate Weber. Just AR is enough.
Yes.
But if you want to calculate the energy, or if you want to calculate a fluctuation determinant term or path integral method, then you need to consider this Degenerate Weber and also hidden topological angle. To obtain hidden topological angle contribution completely, then we have to use this one.
I see. If I understand correctly, the certain aspect of non-perturbatory contribution can be better determined or easily determined by Degenerate Weber rather than
Yes, exactly.
Yes.
Good. I see. I get it. Thank you.
Any other questions, comments? We can also thank the speaker, okay, for the really nice talk, for the discussion. Still eager to actually find more. But before that, maybe we can stop recording. Meaning you can ask questions still afterwards, but I'll probably just stop recording. Thank you so much.
Yeah,
for the discussion and the talk.